Welcome. Today we will visit again the world of numerical methods in order to not solve but numerically approximate some initial value problems. I think it would be better here to say initial value problems. Okay, now many differential equations cannot be solved analytically. For instance, this one, you can try. And we will have to obtain an approximate solution using, for example, numerical methods. The goal is to approximate the solution of an initial value problem. So we need to have an ODE plus initial conditions. In this course, we will only see first order ODEs with the initial conditions in order to solve them numerically. Now, this is very important. When we want to solve approximately an initial value problem, we really need it to verify Picard's theorem, okay? Because this theorem tells us whether the problem has a solution and a unique solution. So we have the guarantee from Picard's theorem that the initial value problem that we want to solve has a solution and it is unique. So we can really try to solve it using a numerical approach, and we have the certainty that we are trying to find a precise, specific solution that exists, and convergence will be easier to be guaranteed. Okay, so how do we will proceed? Well, this is very important. The numerical approximation of initial value problems relies a lot on the geometric interpretation of ODEs. So remember that when we are talking about first order ODEs, we can always rewrite them in this specific form we have here. Okay? And we saw in a previous lecture that this specific way to write them allows us to do this geometric interpretation. What the ODE is telling us is the slope of yt. Y prime is the slope of yt, the function we are trying to find. And the slope is given by this function, f of ty. So we saw in previous lectures that, in fact, an ODE can be seen as a vector field, because at any point, if this is t and this is y, I can select point here and I can draw a vector that is given by f of t, y, 1, because the solution that will go through this point will be tangent to this vector, and the slope of this vector, which is tangent to the line, is given by the slope, is given by y prime t. Okay, so y prime t gives us the slope of this tangent line. I think this is easier with this example. Here I have an ODE, y prime t equals, and this is my right-hand side, which is this function of t and y. Okay? I can pick any number I want here. For example, t equals 0, y equals 10. I could select this point here. So this point is t equals 0, y equals 10. And I could plug in this function f the value 0 for t and 10 for y. And I could do this calculation, yeah? Y is 10 plus the exponential of 0 is going to be, it's going to be 1 plus 1 minus 3 times t is 0, so that's going to be 0, so the result here is 12. So I can plot here a vector. It will look more like t's, I think. Okay. I'm doing it a little bit bigger, okay, just to see it. And this vector is obtained by plotting here 12 versus 1. This 12 is given by f of 0, 10. So what you can see in this example is that we can compute the value of f of ty at a given specific point in this plane ty, okay? And what we know is that given an ODE, we have a vector field that's known, but we also know that solution, we also know that, we also know that a solution of this ODE is an integral curve. That means a curve that is always tangent to the vector field. As we can see here, for example, this curve is always tangent to the vector field. So that could be a solution of the ODE. And this one, for example, that could be also a solution of the ODE. These are all particular solutions of the ODE. Which one do we want to find out? Well, it will depend on the initial condition of the problem. So that's why I told you at the beginning of the lecture that when solving it numerically, it will be very important to select a particular initial condition, for example, this one, in order to guarantee that there is only one solution to the initial value problem. So these ones would not be correct if I need to have this initial condition. I need my solution to go through this point. Okay, so to find the solution of an initial value problem, we need first to rewrite the ODE, the first order ODE, in this specific manner, y prime t isolated in the left-hand side of the equation, and everything else that depends on t and y in the right-hand side. Then I need to have an initial condition of the problem, just one initial condition, because it is a first-order ODE. And from this, we will use a numerical approach to find not the solution yt, we will give up on that, but find a numerical approximation to that. Let's see. As I was saying, numerical approximations of initial value problems do not provide function. I'm not going to find yt. I give up on that, but I don't care. Instead of finding the analytical and perfect solution, I will just find an approximate solution with the desired precision for my problem. Now, what I'm going to do is to find, instead of finding the exact solution yt, I'm going to find only specific values of the solution at the discrete number of points. I would say this is like the crux of the matter. This is very important in all numerical methods. We move from an infinite dimension problem. Remember, yt could be, when I want to find yt, I want to find y at any possible value of t in the real numbers. This has like an infinite number of unknowns. However, in the numeric approach, I'm discretizing it, and the number of unknowns here maybe is 4 or 10 or 1,000 or 1 million, but it's finite. That's very important. That's the idea behind numerical approximation. Now, here we have the steps. First step, very important one, is to have the problem written properly. As we said, we need the ODE to be written in this manner, y prime isolated in the left-hand side, everything else in the right-hand side, and a proper initial condition of the problem. We should verify that this initial value problem verifies Picard's theorem. That's important to guarantee that it has a unique solution. And then we will define the final time of the simulation, the final time where we want to solve the differential equation. We were not doing this when solving it analytically, but now that we are solving it numerically, we will see that instead of finding yt, we will find the value of y at this point, the value of y at this point, and we will do this like iteratively. So first I will find this point, then from that point I will approximate the next point, and so on. So I need to tell the method when to stop. And this would be given by the final time of the simulation that we will call b, for example. And a will be the initial time of the simulation, which here, of course, is the time where the initial condition is given. Normally 0, but we will keep this general notation A. Then the third step is what I think is the most important one, and is discretization. Here is where we move from a problem with an infinite number of unknowns to a finite number of unknowns. I want to find the solution at specific points, and in order to do that, we define the points where we want to compute the approximation given the number of subintervals or the time step. So we can either decide on the length of each interval. In this case, these lengths I was plotting here are these lengths. This will be called h. And at the end, we will have a total amount of n subintervals. So of course, we have this relationship between h and n, assuming that b is the final time and a is the initial time. Then we will see how, but we will numerically compute the approximated values of the solution at t0, and that approximation will be called capital Y0. And we will approximate the exact solution at time t1, and we will call that capital Y1. So the numerical approximation are these values that we are computing here, but they are not a function. They are just a bunch of numbers. They are these values I was trying to plot here, okay? Of course, they will be an approximation. Here I'm just plotting them over the exact solution. It's not going to be that nice, but we will see now. Okay, here's the basic idea. What we will get at the end is, instead of the exact solution that here it's plotted in black color, the black color here is the exact solution, what we call yt. Instead of that, what we will find are these other values, y1, y2, yn, and they are just approximations of the exact value. There is an error. You see here, I have some error here. This is the exact value, but I'm approximating it by this value, y1. And the same for y2. And at the end, what we have is y1, capital Y2, capital Y. These values, capital Yi, they are approximations of the exact solution. And of course, they have an error because they are an approximation. Okay. What if I want to find the solution, I don't know, in an intermediate point like this one? How will I approximate the solution here? What's the value? Well, then you can use what we explain in curve fitting topic. You can use, for example, a linear spline to connect y0 and y1, y1 and y2, and so on. So you can use, for example, a linear spline to connect these lines. I think I can try to do that better. So let's connect these ones. Let's connect these ones. Okay, so you can use, for example, a linear spline to connect these approximated values. And then the value at this intermediate point would be this value, which of course has an error. It's not the exact value. So what only remains now to be explained is how do we compute these values, y1, capital Y1, capital Y2, and so on. Let's see the main idea behind Euler's method. Euler's method is the most simple numerical method to solve initial value problems, but it is very useful and it's used a lot. Let me explain the basic idea here. Let me explain the Euler's geometric interpretation. Now, for Euler, let's say we have the exact solution, yt, and we have an initial condition of our problem. Remember that we are trying to solve y prime t equals f of t y, and we need to have the initial condition of the problem. For example, this one. Okay, so I have my initial value problem. So for example, let's say this is A, and I have this value alpha, and I would like to go from here to the next point and approximate the solution at the next point. What we will do is remember that we divided, this is A plus H, this is A plus 2H, and so on. So let's say I call this T0, I call this T1, I call this T2. These are the discretized points where I will try to approximate the solution. Okay, for the first point, I would define y0. Remember that capital Y is nothing but the numerical approximation I'm trying to find. So it's a number that it's supposed to approximate the value of the exact function at point ti. So of course, for the initial point, I have the initial condition of the problem. Let's use that. So y0 is always going to be equal to y at t0. In this case, sometimes we call it a, okay? So that's the only point, t0, where the numerical and the exact solutions are the same. Because I know the exact solution there, let's use it. Now, how do I compute y1? y1 is supposed to be the approximated value at this point t1. How can I compute an approximation? Well, let's use the geometric interpretation of an ODE. I know that the ODE is giving me at this point a tangent vector. This tangent vector, remember, I'm drawing it very big, I know, it's just to make it clear. This vector can be computed just by using f. In this case, if I'm at this point, I'm at t0, so f of t0, y0, yt0. which is the same as f of t0 capital Y0. Yeah? And of course, this is 1. Okay, this is the slope of the tangent line. And I want to go just this distance. I want to move a distance h. So I will move over this line because I know that the tangent line is a very good approximation of the exact solution if I move a little bit, if I keep very close to it. So I will move just the small distance called h, and I will stop here. And this is going to be y1. This is going to be the value. This is going to be y1. This is going to be the value. Let me write it like this. This is going to be the value that we will use as approximation of the exact solution. Okay, so what we have done is that y1 is equal to, well, we will find the formulas later if you want, but the idea is that we moved from y0, a distance h, following the slope given by f at the previous point. That's what we did. Now, how will I compute the next point, the next approximation at t2, for example? Well, I will compute here using the ODE the tangent vector at this point, and I will move in that direction up to the next point t2, and this is going to be the value for y2. So this is the geometric interpretation. You know that my drawings are not very good, but I wanted to explain it as I do in the blackboard when we are together in the lectures. So this is what is explained in this slide, okay? This is how we advance from one point approximation to the next approximation. I have explained the geometric interpretation. Here you have the formulas, where basically we are constructing here the formula for the tangent line that goes through this point, t1, y1, the tangent line that goes through this point with this slope, the slope given at this point by the tangent vector. So we will use that line to move up to the next point where we want to approximate the solution. Here basically we have that this is t0, this is t1, this is t2, and so on. And we can see in this slide that of course there's an error, it's not the exact solution, but as you may see now, the main idea here is that I can control this value of h. So the smaller the value of h, we will see, the better will be the approximation. Okay? So that's the formulas. In general, we can see that, for example, y2 is computed in this way. And in general, this is the formula of Euler's method. Okay? Euler method computes the approximations using this formula. So if I'm at point yi, I can compute from there the next approximation at the next point. So basically we are at point ti. We know the value of the solution there. It is yi. And from there, we can compute this vector, f of ti, yi. And using this information, we will define which is ti plus 1, the next one, and this value will be used as the approximation yi plus 1. That's the main idea. You have a much nicer plot here, okay, that tries to represent this. So this is Euler method. This is the basic formula. Let's do an example, okay? a numeric example. So let's say we want to approximate the solution of this initial value problem we have here. Y prime t is in the left-hand side, already isolated, and the right-hand side here is this function f of t y. So the ODE is already written properly. Here we have the final time defined where we want to approximate the initial value problem, and of course the initial time, which is the point where we have the initial condition of the problem. Okay, so we have the ODE, the initial condition of the problem. As homework, I propose you to check that Picard's theorem can be applied and that we can guarantee that this problem has a solution and it is unique. What we will do in this lecture is to use Euler's method with a time step of 0.2 in order to approximate the solution of this initial value problem. Okay? So we start with the, I will try to write here the first steps, okay? Y0 is always going to be equal to yt0, in this case y0, which is equal to 1. So we know that. At the initial condition point, at where we have the initial condition of the problem, y0 is always the exact value. It's the only place where it's not an approximation but the exact value, because we have the initial condition given there. Okay? Now, how do we approximate the numerical solution at the other points? The first thing is to decide which are the other points, and that is done using the value of h that was given to us. Okay? So, if I have a step of 0.2 and t0 is 0, the next points will be 0.2, 0.4, 0.6, 0.8, up to 1, because 1 is the final time. So the objective here is to find y1, y2, y3, y4, and y5. Because y1 is going to be the approximation of the exact solution at t1, and y2 is going to be the approximated value of the exact solution at point t2, and so on. So we start from y0 equals 1, and we need to compute the other values. The main formula of the method, remember, is that yi plus 1 is equal to yi plus h f of ti yi. So what this formula is telling us is that we move from yi a distance h following the direction given by the tangent line. So let's use this formula to compute, for example, y1. y1 is, okay, y1 means that in this formula here, I is 0. So here I have y0, t0, and y0. Let's do that. I have here y0 plus h times f of t0, y0. Now, y0 is equal to 1. y0 is equal to 1. So that's 1 plus h is equal to 0.2, 0.2. And then f of t0, y0, remember that t0 is 0. And as you see here, f of t y is t times y. So f of 0, 1, which is the value of y0, is 1. The result is the product of both, so the result is 0. So 0.2 times 0, 0.2 times 0 means that this term is not there. So the result is 1. Okay? And then we would proceed in the same manner to compute y2 and so on. In this slide, you have the table, the summary of all the formulas. We did this step in the previous slide. y1 is equal to y0. Yeah, we did this. And as we had this 0, this term was vanishing and the result was 1. So you can check here, try to do it by yourself, and then check that you get these results as approximations of y2, y3, y4, and y5. Okay? In this specific example, we know how to compute the exact solution of the problem. It was written here. Okay, and as we know the exact solution of the problem, we can compare the errors, we can see the errors. I think it's better to see that in this figure. We are plotting here the different errors, okay? In the initial point, the error is 0, but then at the next points, the error starts increasing. The error at the final point, at the final time, is also called global error, okay? And what we will see now is two very important definitions, the local error and the global error. The local error is the residual, or local error is the error committed when computing yi plus 1 from yi, but not taking into account the error already accumulated in yi. So, for example, this difference, let me explain it better. The local error is the error that we commit when computing the solution, the approximated solution at yi plus 1 from the previous one, but not having into account the error that maybe it was already accumulated in yi. Okay, that's what we call local error. On the other hand, what we call global error is the overall accumulated error of the numerical solution at the final time. So the global error is the difference between the numerical approximation at the last point is always Tn, and the exact solution at that point, that we also call it B sometimes, okay? So these are two very important definitions, local and global error. And what we will see now is a very easy way to derive the local error. The ODE that we are trying to solve is this one. One way to try to solve this is integration, yeah? We could try to integrate here the integral between ti and ti plus 1 with respect to t should be equal to the integral of this function with respect to t. Why not? That's one way to solve this ODE. Why we did not do this before? Let's see. The integral of the derivative, they are inverse function one to the other. So the result is yt. Yeah, but as we have a definite integral, we need to use Barrow's rule, and what we get is this. The result of this integral here is y at ti plus 1 minus y, the exact solution, at ti. Okay, what about the integral in the right-hand side? Well, if this ODE was solvable analytically, then this integral will be possible to compute it exactly. When we say that we have an ODE that cannot be solved analytically, this means that this integral is not solvable analytically, so we need to use a numerical approach. In the case of Euler method, this is exactly the same as using here to approximate this integral the simple rectangular left rule. I think it's one of the simpler rules we saw. So here, the left-hand side remains exactly the same, and the right-hand side, instead of this integral, we are approximating that integral using simple rectangular rule, which is to evaluate the function at the left end of the integral, okay? So between ti and ti plus 1, I'm just using simple one interval rectangular rule. So I'm just evaluating the function at ti and y of ti. We know that the simple rectangular rule has a local error which is order of h squared for the simple rectangular rule. So therefore, what we have here is that we derived our Euler method. You can see here that for the exact solution, this is an equal, but for the approximated solution, what I'm doing, I'm just copying this. Let me copy it in the same order. F of ti, yi times h. I'm dropping this term when using the approximated approach, and I have an equal sign here. But as I'm dropping the error, I'm dropping this term here, these capital Y's are not anymore the exact solution, yeah? So somehow using the simple rectangular left rule, we derived also the formulas for the Euler method, and we proved, which is very important, that the method is, the local error is order of h squared, okay? Now, this is the local error. What about the global error? Well, the global error is the overall accumulated error after n time steps. So, under certain hypotheses, for instance, that the solution is bounded, has a bounded second order derivative, we can simplify how to compute the global error as the number of time steps times the local error. So what I'm doing here is to compute the global error as n times the local error, which is order h squared. And we find out that, okay, n is just b minus a divided h. That's n. So, of course, this h will simplify, and this does not depend on h. So it's a constant that does not depend on h. So the result is that the global error, this is very important, the global error has this order, and we will say that Euler's method is linear. We will say that Euler's method is linear because its global error is linear. Here you have a summary of what we did. In general, we say that a method is of order q if the global error is of this form. So for Euler, we say it is linear or order 1 because the value of q is 1. We have seen that when the local order is q plus 1, then the global is q because of this h that is dropped here. And as a remark, we can see that when we have a linear method, it will happen that when I divide by 2 the value of h, the error will also decrease dividing by 2. If I divide the value of h by 10, the error will be divided by 10 because it is linear. That is what I wanted to explain today. Thank you very much and see you in the next lecture. Bye-bye.